Hello everyone. Um, I'm pleased to make this presentation here. I'd like to thank all of you for this opportunity. Today I will be talking about neural network and its application for classification of point clouds, which we do in BSF Swiss Photo. The current presentation contains some theoretical part about statement of the problem, architecture of the simple network, and a step from processing images to processing point clouds. Then there is a part with real results for photogrammetric point cloud, for LiDAR point clouds. Then there are parts of statistics and duration of processing and the summary. So which task do we solve? What do we have as an input? This is a part of point cloud, which is probably a pre-processed output from a LiDAR scanner. We have some trees, some power lines, some masts, and so on, but we don't know where is what. And we want to get this. We want trees be marked as trees, ground as ground, and etc. So in a formal way, description of the task is the following, that we have point clouds unlabeled, which are results of LiDAR scanning or computed from images. They contain coordinates of millions of points, and usually with other features like RGB or intensity, etc. And via processing, we want to reach labeled clouds, which additionally will contain some new feature called label of class. For example, 0 as buildings, 0 as ground, 1 as buildings, 2 as vegetation, and so on and so on. Our solution of this task is done via KP-conv neural network, which stands for kernel point convolution. It was developed in Paris Tech School of Mines in year 19th, based on logic applied for image processing. Originally, KP-conv was built for classification of 3D scans and indoor clouds, so adaptation for ALS was required. Now it's successfully used in BSF Swiss Photo for real projects and gives awesome results. Working with neural network consists of two steps. Step of training is learning what objects of certain classes look like and saving this information as an enormous set of matrices. And this information can be something like vegetation is something with high values of echoes, or power lines are linear objects with, which are close to horizontal. Application step is using of the acquired knowledge for classification of unlabeled clouds. However, this is not magic. Classes and features must be the same as in the training step. Why is neural network called neural? It's because the basic element of the network is a neuron. It's a simple mathematical model which processes input numbers in a certain way. It takes inputs, some numbers or whatever, multiplies it with weights, and sums everything up. So getting a weighted sum, actually. Then applying activation function and sending all of it to the output. In case of processing of images, it looks like the following. We work with intensity of pixels. So we perform element by element application of inputs with weights, inputs with weights, sum everything up, apply activation function, and this is how we get answer for this pixel here. If we have a neighboring neuron, it will process another pixels with the same kernel, and we will get another pixel here, like this. When we process the whole image with the kernel, we will get a new image, which will be a result of this level. When we assemble neurons into layers, we get a construction which is able to detect features from bigger and bigger neighborhoods. For example, this pixel knows what happens in this area, but this pixel already considers the whole more than a half of the picture. So information comes through the network from left to right, and after collecting information from all those pixels, we distribute features back to every point where it's possible to calculate its value of class to make a prediction. When we have true values of classes, we can calculate differences between predicted value and true value. And since we know how does difference depend on weights, we can introduce correction into the weights so that the result will be closer to the optimal. Making these steps, information forward, correction back, information forward, correction back, a lot of times, we go to a situation when difference is minimized. This is what is called training. This is why we need true values of classes. After performing training, we can check which features did every layer learn, and we find out that different layers, in case of face recognition, for example, learn different features of different levels. For example, low-level features are learned here. These are some edges, dark spots, and so on and so on. The next levels will learn mid-level features, which are combinations of these features. They are eyes, ears, noses, and so on and so on. Even higher level features are combinations of this one. These are already facial structures, and bigger and bigger and bigger. All of this for images is possible because of regularity of the structure of the neighborhood. It's always possible to know which pixels are neighbors of the pixel, and their number is always constant. But what do we do in case of irregular structure like a point cloud? How do we detect neighbors here, and how do we understand what do we do with the features? So again, in case of images, we build matches between pixels and weights, multiply them, create a linear combination, and say that this sum is what is characterizing the neighborhood. In case of point cloud, we have points which are having continuous coordinates. Let's say we will take a look at a 2D object, not a 3D. But our task in this case will be gathering in the point A all the information which is in its neighborhood. And let's say we have a set of points in shape of number 7 there. Each of these points has some coordinates and has some intensity value. and we want to collect this information in the point A. We say that we locate weights in kernel points, vertices of some regular structure, for example, hexagon. And these weights are having now some spatial coordinates. And then we compute distances from each point of the cloud to every kernel point. In this way, kernel points set up some kind of a grid, which makes possible to provide a value of weight for every point of our cloud, and as a result, to compute a weight of every point of our cloud. When we get a weight of every point for of our cloud, we can multiply it with features, and the same as here, get a value which characterizes the whole neighborhood as we wanted. After that, when features are collected from one level, they are passed to the next level, and again, the same as with images, the deeper level, the bigger the area which can be considered by a single neuron. Then features are distributed back to the original points, and their classes are derived, so that in the final picture you can see something like this. There is a car standing somewhere on the asphalt, there is a fence, some kind of a building there, a tree here, and so on and so on. In comparison to the images, we also can say here that this is a 3D case. The lower level, we're finding some simple structures like what is ball, what is cone. Next level layers were working with more complex structures like what does a roof look like, what is a tree, and so on and so on. So now we will see more pictures, more real results. For example, here we have a photogrammetric cloud, which has features of colors RGB and intensity. And it has a very high point density, 1,000 points per square meter. You can see that even some small objects like balls or some bushes are present here. But we don't have so much features, only 4 of them. As a result, we get the following classification. It's only binary, ground and non-ground, but we can see that ground is red, and all cars, all roofs, all bushes, all fences are blue, which means they are non-ground. A bigger area, a block of the village, and again roofs and trees and cars are detected very nicely. You can see that there are some cars here, some cars here, some cars over there. So yeah, looks great. What can we do to improve our results? Because in this case we were working with binary classification, ground or non-ground, but always we have situations where we have more classes expected, so we want to understand what can we do to improve our results. We can involve more features, for example. Here we have visualization of how does echo feature look like, and you can see that it can be a very good feature for detection of vegetation. Vegetation always provides higher values of echoes. And there is a feature of intensity too. It's also a very useful thing. Okay. We can also perform iterative processing, train a coarse model on small data set, apply a model to classify a big data set, manually fix mistakes, and train a model on big data set, we get fine model, which is ready to perform fine classification. This way we detected the power lines. As you can see, there are some vegetation and trees which were not a problem. Power lines were detected very good. One issue happened with the power line here. Network thought that this point belongs to the mast, while it's part of power line, of course. The same here, a border between power line and mast was not detected very good, but it's only several points. In case of general scene, we have an issue only with those balconies on the roof floor here. They were not very clear about are these balconies roof or are they part of facade. Cars are detected very good. As you can see, only points near the ground are slightly unsure. Cars are detected in the neighborhood very good. On the closer look, you can see that they are detected very confident and no points are mistaken. The only issues with cars happen when there are problems with reflectivity. So this car lost some points from its bonnet, and the network didn't understand what is this object and assigned another class to these white points. Taking into account all of what we discussed, our accuracy for classes like ground, building, and non-ground is good. Our accuracy for power lines is exceptional good, because they are just straight objects, linear objects, which are usually parallel to the ground, so they are described very good. Masts sometimes have different shapes, and they are not represented very good in the data set. There are not so much of them, so we have some lower metric value for it. And processing times were about 80 hours for the biggest point density. Reducing point density helps a lot, even for a very big cloud of 300 kilometers square. We get only 70 hours required for processing. So as a summary, neural networks truly are a great tool for geodata processing. It brings the next level of expertise, which traditional methods are incapable of. For example, even such classes as power lines can be detected. Usage of this tool requires a piece of already processed data for the goal of training, but with technical progress in the area of parallel computations, the capabilities of neural networks will only grow on. Thank you.